Hi everyone. In this series about the universe, our today's topic, which I suppose would be uh, rather interesting for most people, is do aliens exist? So let's just move straight away to our discussion. So we'll start the with the discussion about what is life, because if we want to find life somewhere in the outer space, we first need to define what life is so that we can really understand what we expect. And then we'll briefly discuss the this concept of alien in the sci-fi culture over the last several decades, and how it has become such a important question for humans, this alien life. And then we will discuss some latest developments in astrobiology, some recent research findings and their implications. And we'll move next to this exoplanet detection methods and techniques. I will give you a brief overview of how astronomers find exoplanets and what could be in the near future, what kind of developments we expect to have. And in the last, we will discuss the possibilities of can life exist, and supposing it exists, so will will we be able to find it? So let's just start with what is life itself. So honestly, we don't know what life is, in the sense that actually life is a very how to say, um, it's not easy to explain life, even scientifically speaking, and I tell you why. So before we I explain you that, so let's just first define uh, life. So according to NASA's definition that they often use, that life is a self-sustaining chemical system capable of Darwinian evolution. So life should have two essential components. First, it should be self-sustaining, and second, it should be capable of evolution. So, because if something is not evolving, then it's not debatable whether it's life. So the problem with life is that life is actually a binary measure. So it means that it's a qualitative measure whether something is alive or not. So the answer is either yes or no. It's not in between. You can't really ask, or you can't really say that certain uh, life being is 50% alive, or you can't say it's 70% alive. It's either alive or dead. So, and the problem with the life is that life is actually a collective property of biological systems. So it's not an individual thing that you can just study. So I give you an example. So for example, humans know very well how the circulatory system works, how uh, respiratory system works, and how other systems like digestion, human metabolism, and all other processes work. But how these processes really combine, or let's say relate with each other to give a collective property that is called life, it's not very easy to understand. And this is a big question. And second thing, we are dealing with uh, uh, with life is that one problem is that biology is very different from the physics and the chemistry. So that's why it's a different branch of science anyway. So there was one effort by a physicist. A lot of people know about him, Schrodinger, who is famous for his Schrodinger's equation in quantum mechanics. He is known to be kind of a father of modern quantum mechanics, and he tried to understand life in the in terms of physics. And then he came to this conclusion that it's a collective property of many systems inside a human, so it's not easy to explain um, how life works from the point of view of physics or chemistry. We know how individual systems work, like circulatory system or many other systems in the animals. But how these systems collaborate or correlate with each other and work together to give this collective phenomena what we see as life, is not very easy to understand. So obviously you have to read the biology books. So yeah, and life is confusing. Even I mean, the word life has many meanings. So we are talking about the biological life here, but of course people talk about in the ethical sense that okay, I have a good life or I have a bad life, or yeah. So so these questions, that what is life, it's both ethical and scientific at the same time. Of course we are dealing with the science here. So and then one important thing about the life is that it looks different in the different species. So for example, life is more intelligent in animals and probably a bit passive in plants or the microbes. Yeah. So when we are looking for life somewhere outside the universe, we should be open to all possibilities. We are not really looking for some human-like aliens. It could be anything. So okay, so whether life is active or passive, but anyway, they all share one single biochemical component. So that biochemical component is of course the DNA and the proteins and RNA and yeah, these stuff. So keep in mind that when we are looking for life in the outer space, we can only look for the life we know. So that's another thing that we should keep in mind. And so there is a question that can life be a spectrum rather than a binary 0 and 1? Mean that can life be just either dead or alive, or it could have like a whole spectrum, let's say 30% life or 50% life or 70% life. Can we say like this? Actually, we don't know. So let's just move to the next slide. That's aliens in sci-fi. So there are huge debates everywhere in the science circles as well, but probably I mean, more so in the media about aliens and what do they really exist. So we don't know if aliens exist, but they surely exist in people's dreams. They exist in poetry. They exist in the novels. They exist in the movies. So all of these, at least they exist here. So so for example, a lot of people know about the Star Trek, and then some other movies or series like Alien and Arrival and etc etc. So so actually this concept of aliens became very popular in the 60s, I suppose, and mostly I would say because of the Carl Sagan. So so then the Saganism, it just moved to Hollywood, but I think it was not represented very well in the Hollywood, because probably the people in the Hollywood were not scientists, or they or maybe they just really didn't care about science. So a lot of time there is a lot of confusion when we say alien. So alien just mean that okay, this should be kind of some humanoid robot like creature, and they come from the sky. They have a ship, they have a kind of a spaceship, and they can come on earth and do something and then go back in the night. And then alien invasions, wars, alien threats, they are often glamorized in these movies and novels and so on. Actually, scientifically speaking, I think if in the outer space if we should really be looking for something, it might not be alien-like. I think the microbes are more probable if we are really looking in the outer space, because I will explain you in the next slide why these organisms are more probable than this humanoid aliens. So yeah, but let's just agree that this aliens in the sci-fi culture, it also had some positive aspects. So the positive contributions are, of course, have to be mentioned. So first of all, it's really inspired the space exploration itself. So it's inspired the scientists, and it sparked the space exploration. It encouraged the human curiosity to think beyond what exists and what we can see already, and also it encouraged for people to study the philosophical and ethical implications of if there is an extraterrestrial civilization. Then of course the question arises how we should live with them, how we should treat them, and what should we expect from them, and what should we offer them. So all these questions. So yeah, it's a meaningful debate in so many ways. Okay, so let's discuss some recent discoveries, some what's happening in the domain of astrobiology. So astrobiology is actually okay, very generally speaking, it's just looking for the some biological life in the outer space, on the planets, and in well, mainly in the in the Milky Way, but maybe outside the Milky Way as well in the future. So and so this whole idea of mm, okay, let's not use the word aliens again. Let's just call it extraterrestrial intelligence. So this whole concept of extraterrestrial intelligent life, as people really started to take it seriously in the 60s. Although the idea is not new, of course, it's I mean, people always wondered that are we really alone in the universe, so it's not really a new idea in itself. So, but the research started obviously when it really became part of the human social culture, and it really became an important question for humans. So, and also there is a reason that we think that we live in our solar system. So, what is a solar system? A solar system would typically consist of a central star, which they call sun, and then there are some planets that are orbiting around that sun. So just like we have our solar system, there are so many other solar systems in billions inside the Milky Way, and outside the Milky Way in other galaxies. And in the previous um video, we saw how big is the universe, and how many galaxies are there. We have the galaxy clusters, and yeah, so it's unimaginable. So the possibility of life existing somewhere in the universe, theoretically speaking, it's really hard to deny that life would exist somewhere, unless you are convinced that life is rare and it's special to Earth. So yeah, we don't really know. Anyway, till now, NASA has confirmed that more than 6,000 exoplanets have been found. So, from astronomical point of view, what do you really need to sustain a life is a habitable planet. So, a habitable planet really means that it should be a planet that should not be very hot, that should not be very cold. It should have the right temperature. So let's just call it Earth-like planets. So we have found a lot of them, and so these planets do exist, but we haven't. We don't have the technology to really go there physically and see what's happening. So what we can study is from far away, and we can make some observations and then see. And I think these observations will become better and better in future. I will be discussing this very soon. So I think, as we discussed previously, that the microbes are really ideal candidates if we are looking in space. That's because they are extremely resilient, and they can survive extreme environments like high radiation, low pressure, or high pressure, and extreme heat or cold, and or acidity. Yeah, these kind of environments, a lot of microbes can survive. So rather than looking for the humanoid aliens, I think the microbial life is much better candidate. So the recent findings is that yes, there have been some Earth-like planets found around some other in other solar systems. We call them extra solar systems, and these planets are called exoplanets. So and few of those exoplanets are Earth-like. Means that they have conditions which are Earth-like. They have atmosphere. They have the right amount of heat and the right amount of radiation, light, all the things. I mean, probably not exactly identical to Earth, but very close. So the recent studies in the last 10 years or so in this astrobiology, they have been morely related to the moons actually, because the closest ones, the closest planets to us are our own solar system planets like Jupiter or Saturn or Mars. So and all so just like we have a moon on the moon that belongs to our Earth, these other planets, they also have moons, and probably more than one. So so for example, this recent research actually last several years ago, they found that this surface oceans in on the Enceladus. Enceladus is a moon of probably Jupiter. I'm not sure, but anyway, it's moon of one of the planet, and so in those oceans they also find the phosphorus, and they also find the complex organic molecules. Now, phosphorus is really important for human or animal, let's say their bone structures. It's really important element for life, and also since our life is a carbon based, so finding a complex organic molecules that can help make the proteins and other structures like DNA, they are really important. So I think this would discovery, that under the surface of Enceladus there are oceans of water with these kind of chemicals present in them. So this was from the mission Cassini, and just like we had explored Enceladus, people also are exploring the Titan. That's the Saturn's moon. Yeah. So the Titan, it also in its atmosphere it has been found some organic molecules and the methane. So that's also interesting because these are also important chemicals for life. So and another mission to the moon, Europa, is also an interesting case where people have find the surface ocean. So yeah, so actually we started pretty much from our near neighborhood, like the Saturn and Jupiter and Mars. So this is a good start, and I think if we can so in these in the a close neighborhood, we haven't really found the real existing life, but we have found some precursors, like some chemicals there that can be the building blocks of life. So I think the future exploration will be keep going, not only in the near neighborhood, but also try to make it far away, and yeah, to see how it what it reveals. So there are a lot of missions. So first of all, you know about the Mars, right? That the Mars has a lot of rovers already, and some orbiters from a lot of countries like US, China, India, and probably more as well. Um, so these rovers, they have very specific instruments to analyze the dust, to analyze its atmosphere, find the chemical composition of these objects, and that can really give you an idea of um, what can life uh, can the life exist there, and it can also give you idea that if you are available to make it habitable in future. So the possibilities are of course there, but possibilities versus capabilities, that's just another question. Anyway, so the Kepler, I think earlier, probably the early mission to find the exoplanets was Kepler. So Kepler found, I'm not sure if it's still operational. Probably yes. So it has found most of the exoplanets, at least in the start. But recently we have other telescopes and missions as well. So okay, so the Kepler is one, and then the second is the planetary moon missions, as we discussed before, on the Titan, on the Europa, on Enceladus. So these missions mostly belong to the European Space Agency, and the and the US Space Agency. Um, and then in the future, it's also expected that there will be some return of samples from Mars, at least. So these are also planned by the European, American, and the Chinese, or even Japanese missions. And then the recent James Webb Space Telescope, it also it's a infrared telescope, and it also uses infrared spectroscopy to detect the molecules, um, and so what kind of methods we use, I will explain you in very soon. And then there is a project called SETI. It's the search for extraterrestrial intelligence. It's they use radio and optical telescopes, so it's a big project, and a lot of people who are very actively working in this search of extraterrestrial intelligent life. So it's a really big project. And then some future missions are expected, like the Nancy Grace Roman Space Telescope, hopefully in the late 2026. And then from the NASA, dragonfly, which will be used probably for some chemistry of the planets that I mean it's related to the extra terrestrial life. And then the habitable worlds observatory, of course, the list goes off and on. It keeps going. It's not a complete list by far, so there are more missions and projects on the way that I might not have mentioned here. So yeah, so this is just a view of few of the telescopes and observatories that look like. So this is James Webb Space Telescope. This is the Kepler. This is TESS, and this is upcoming big observatories, big optics telescopes on Earth. So one is TMT, 30-meter a telescope which has the aperture about 30 meters. So this another is the European ELT, extremely large telescopes. So these are very big telescopes on Earth, and they have very high resolution power, and with the right instruments attached to these telescope, I expect a lot can be done in the field of astrobiology as well. So yeah, let's just discuss how we find the exoplanets. Okay, let's say the other solar systems, how we find other solar systems like our own. So I think probably one of the most commonly used methods is called the transit method. So the transit method is okay, here in the figure on the right side you see this panel. So this transit method, so it really tells you that if okay, this blue dot is a planet and it's moving around a sun, a star, and okay, what happens is that when it passes in the front of the star, then the brightness of the star goes down, so it will have a dip. So you see here, so there is a dip here, so there is another dip here. So these periodic dips can tell you that okay, if the brightness of a star is going down periodically, then it means that there is a planet revolving around that star. So, and this method is very convenient and very useful for and it has many advantages. So first of all, because the planet is in the front of the sun when you observe it, so it can really give you an idea of the planetary atmosphere. So if the planet has an atmosphere, just like on Earth we have an atmosphere that has oxygen, nitrogen, gases, and helium, and other some small trace gases. So these atmospheres can be resolved. So, and we can also calculate how much far is the planet from the star and what is the planet size. So a lot of parameters of the planets can be determined using this method. The second thing is the radial velocity method. So radial velocity method is, so okay, so if you know about, so probably we have like the common people think that that the sun is the center of the solar system and everything revolves around the sun. Actually, that's not true. Keep in mind that the planetary in the planetary systems, everything rotates about the center of mass, not about their sun. So what happens is that usually the star is much more massive than the planets. So the center of mass almost lies on the star itself. So the star does not seem to be rotating. But actually, if you see it very precisely, you will find that even our sun, it 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 wobbles. It wobbles because the planets around the sun and the sun itself, they are all orbiting the center of mass, and the center of mass is very close to the sun, so it does not really make a big orbit, so the sun just seem to wobble a little bit. So this method, so this kind of motion on the right and on the left, it's called wobble. So if you see that there is a star that is wobbling, it could mean that there is a planetary system involved with that. So that's our second method. But keep in mind that this is more useful for the massive planets only, because the massive planets can really create a lot of wobble to the parent star. If the planets are too small, probably there won't be a significant wobble to be detected. And the third method is simple imaging method using the coronagraphs, or what we call them, the star shades. So what happens is that when you take an image of a star, then you block certain parts of the star at certain frequencies. If you block certain frequencies, then you will find that the planet become visible. So for example, here this is the planet, this blue dot, and you see the star has become dim because we have removed some of the light. But when we dim some of the light, this planet becomes visible. So this is a very extremely challenging method, but this method is very useful because it gives you a lot of details about the star. It can give you idea, because what you are seeing is that actually when you remove certain frequencies, then what you find that that you actually observe the light that is reflected by the planet and coming towards you. So it can give you a good idea of a planet's temperature and its atmosphere, and maybe a lot of other parameters as well. But keep in mind that this is only suitable for large planet orbits. So the large orbits, it means it's more easy to detect, because if the planet is too close, it's not so easy to detect the planet, because you have to block certain amount of light. And so the challenge here is that also you need very large optics. You really need very big telescopes, and then you have to use the coronagraphs or the star shades to block certain frequencies. And and then the last method is the direct astrometry. So astrometry means really to find the changes in the positions of objects in the sky. So let's say there is a wobble due to planets. So the star is wobbling, and this has this motion, this left and right motion. So if you can directly, you don't measure the planet, but you can measure the changes in the position of the star, and that can give you an idea that this system might have a planet. So one example is recently the Gaia. So the Gaia has released large amount of astrometry data that can be used to detect exoplanets. So as we discussed, these are 4 basic methods. Of course, these are not the only methods. There are other related to the Doppler shifting and or the gravitational lensing. I have not discussed those, although if you are really interested in those, you can read more about that. But one thing we have to keep in mind, that all these methods are not perfect, as we have seen that certain methods have certain strengths and weaknesses. So what we can really do is that we can use multiple methods on each systems, but then it's not even possible because not all the systems are same. So for example, this radial velocity methods is good for if you have the massive planets or orbiting a star, and yeah, so it depends. Anyway, we move on. Okay, so one big actually all this idea because if you are really looking for something, you have to put it in the scientific in a framework. So this scientific framework actually came, this idea, from the Drake equation. So actually this equation can tell you that, okay, in a galaxy, okay, let's say the Milky Way, we usually solve it for the Milky Way, that if you know how many stars are in the Milky Way and how many stars form in 1 year, and then how many of those stars have the planetary systems, and how many of those who have the planetary systems have the planets like Earth, and then how many of those who can have the planets like Earth, how many in a fraction of those can have intelligent life, and other parameters, and also how long a civilization can exist on those planets. I mean, for the time that they can be communicated. So if you know all these parameters, you just simply multiply and calculate this n, this capital N. So this capital N gives you the number of alien civilizations that can be found in the Milky Way. So so this N is the number of civilization. This parameter R star is the star formation rate. We know that the Milky Way find few stars in 1 year per year, let's say 2 stars or 3 stars. And then this Fp, it is the fraction of the stars with the planetary system. This parameter is usually 1 because almost all the stars have the planets. And this multiply by this Ne. So this Ne is the number of planets per star that are environment suitable for life. Okay, let's say Ne is the fraction of is the number of planets per star which are Earth-like. And then Fe is the fraction of those planets that can sustain life. So Ne is the number of planets that can have life, and Fe is the fraction of those Ne planets that can sustain life. And then Fi is the fraction of those Ne planets that can have intelligent life. And then Fc is the fraction of the civilization are those planets is the fraction of those Ne planets that can sustain a civilization and can have the communication. Okay. And then this L, this is just the lifetime of that communication. Now these are the parameters. If so few of them are very hard to constrain. So let's say we know pretty well about R star, this one and this one. So R star is usually from, let's say, 2 to 5, and Fp is usually 1. But all these other parameters, they are not very easy to find. So one question is obviously this L, the lifetime that a civilization will interact. So a lot of researchers also you have to study the history of the civilization, that how long civilizations exist and how long they are able to communicate. So usually okay, so in the bottom I gave the values of these parameters. And by the way, these parameters can be summed, they can be grouped together to find. So for example, this R star Fp Ne, we can write it as N is a number of habitable planets in the given volume of the universe. Okay, and these last three they can be given F as Fbt, which is the likelihood of the technological species arising on one of these planets. And of course then L is the lifetime of the civilization communication. So by giving these values, I write in the bottom. So for example, Milky Way makes about 2 stars per year. All the stars has planets, so Fp is 1, and usually at least 3 planets are can be considered as habitable, so Ne is 3, and then Fe is almost 1, and this fraction is very small or even smaller than this, and Fc is 0.2 and this L, the lifetime of the civilization. So historians and scientists believe that it's order of few hundred years, let's say 300 to 500. So now if you use all this value, you find that the N, okay, it's not visible here, but the N is very small. So the N is 10 to the raise power minus 13. So it's a rather small number, which tells you that we are probably alone in the Milky Way. But is it? Actually, this equation cannot be taken seriously, because if life is rare and life is dramatic, then all these fractions do not make any sense. So it just means that it's just a let's say, a probabilistic answer that you can get from the Drake equation. And of course you can modify this equation according adding new parameters and to have the better estimates. Okay, and in the last, so we come to the possibilities. So the question is, if intelligent life is common, okay, by the way, going back to the Drake equation, so if you can use some optimistic values of those parameters and you can increase the lifetime of a civilization, you can find that n is very high, more than several thousands. So that can give you a very optimistic answer that there should be more than thousands of civilizations in the Milky Way. But again, I told you that's a probabilistic in a framework. You cannot take it seriously because life can be very special. And so even if there are a lots of planets that has a lot of stars that have a very high fraction of planets that can sustain life, that does not guarantee that there will be life, right? Because the life could be rare. So this is this Fermi paradox. So he says that, okay, if n is very high, if the intelligent life is so common, where is everybody? Why don't we see them? And there are several answers to this paradox. So let's take them one by one. So first thing is that there are lots of constraints. One is that obviously we can only explore the nearby planets, physically speaking. We can probably go to some nearby planetary moons or some nearby planets, but we cannot go far away from Earth because we don't have the technology, we don't have the capability. So that's one reason, that the physically we are not so much advanced. Then the second problem is that the civilizations are usually thought to be self-destructive. So it might be possible that there were a civilization and those are already gone. Just like we had the dinosaurs, and then people say a big asteroid came from the space and hit the Earth, and all the dinosaurs were destroyed. So yeah, so or the civilization are self-destructive, mean that they will always find a means to self-annihilation. So that's a big problem. And then there is a possibility that they do not choose to interact with us. So there are civilizations, they have the technology of communication, but they just choose not to communicate with us. That could be one possibility. And then this is very important. We are either too early or we are too late in this process of evolution. So if we are too early, it means that there are chances of civilization, but by the time they arise, maybe we are already gone. Or maybe we are too late. There were some civilizations and they are already gone. And then a big problem, we are limited to the observable universe. We don't know how big is the universe, and we don't really know what to expect beyond what we see. So, and the last very important question is that the life could be rare itself. So even if there are a lot of Earth-like planets, maybe it is only this Earth that has the life. So, and then also another thing is that the life itself could be non-biological. As I said, that we are always looking for biological life like us, but the life can be non-biological. For example, in the recent times, a lot of people say that AI will replace humans. So suppose if AI replaces humans, that really means that AI is life, right? But it's not biological. It's other form of life. So these are big questions. These are speculations, possibilities. We don't really know. We have to accept it, and I think in the coming, let's say 20 to 25 years, we will get a lot more close to answer a lot of questions. At least we will have big capable telescopes. We will have better understanding. So 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 this is an optimism that the coming time will be it will bring some answers to some of these questions at least. So yeah, so with this I think we finish. I hope we it was kind of an overview of is there a life, and I think we have no clear answer, and yeah, so this is for now. So hopefully we'll see in another video with another topic. So see you. Yeah, okay, bye bye.